Good morning, everyone. So we'll start with the previous lecture now. We were doing density of states in 2D, and in the previous lecture we have done till here that E equals to EC plus EQ1 plus H cross square KT square upon 2mc. Till here we have done, where this EQ1 is what? EQ1 is the energy of the first ring that we are talking about. This is the individual energy of this ring. Okay, we are not talking about with respect to everyone, this any other reference point. This is the individual energy of this ring in the z direction. This was kz, this was ky, and this was kx. Okay, so we'll proceed from here. Energy we have found out. Now next thing what we have to find, we have to find density of states. So for that we need to find out the total area available between kt and kt plus dkt. Okay, so if you remember the diagram, I'm talking about the top view. In the top view, what we were having this thing. This was the diagram. This was the kx direction and this was the ky direction, and this is the first thing that we are talking about, that is due to the k vector, and this was due to the k plus dk vector. And kt is what? Kt was this, and if we are talking about kt plus dkt, then we have to take it till here. Okay, so this is kt plus dkt till here. So what is the area available between kt and kt plus dkt? This is this region, and we will talk about only the positive half. Okay, we will talk about only the allowed region. So the shaded region which I am talking, this region we will be considering only. So the total area, now what the thing is, why we are talking about the area, because now we are talking about a 2D structure, so we will not consider the volume here. Initially what we were doing, we were considering the volume, because we were having a sphere, we were having a 3-dimension structure. But in this case now we are in 2D structure, and 2D structure will talk about the area. So what is the area that is available between kt and kt plus dkt? That is this region, shaded region. So that we can write that the area as, it will be now what? This is the quadrant. This is the quadrant of this disk. Actually this is what? This is disk. Okay, so the quadrant of this disk is, because it has x and y direction. Okay, so the quadrant of this disk is 1/4, and now what will be the area of the disk? Area of the disk is 2 pi r dr. So in our case it will be 2 pi kt dkt. Okay, dkt is what? Dkt is the thickness of this disk. Okay, dkt is the thickness of this disk, and kt is the radius. So 2 pi kt dkt, this is the total area available. Now what is the area occupied by one state? What is the area occupied by one state? The area occupied by one state is given by, it will be given by pi by lx, pi by ly, because now we are talking about 2 dimensions. Okay, only lx and ly are remaining, z dimension we have already reduced. So this is the area occupied by the one state. Now we have to find the number of points. So number of points lying between kt and kt plus dkt. To find the number of points, I denote it by capital N, and the number of points will be, it will be your n equals to total area divided by the area occupied by one state. So total area is 1/4 multiplied by 2 pi kt dkt divided by the area occupied by one state. It means pi by lx, pi by ly. Okay, this is the area occupied by one state. Now since we are talking about the number of points, or we can say the number of allowed states, for the number of allowed states, now we have to multiply it by 2, which is due to the Pauli exclusion principle, because for according to Pauli exclusion principle, in a state there can be 2 electrons. Okay, so we are talking about, since we are talking about the electrons, so we can say the number of states available to the electrons will be twice, so therefore we have multiplied it by 2. So this 2 is due to the Pauli exclusion principle. Now you can cancel out the things that are cancelling out. This pi is cancelling out, so we get n equals to, we get the remaining terms are kt dkt and divided, and this Lx and Ly I am taking in the numerator, and we have the pi here. Okay, this is n what we are getting. Okay, now we have to find a density of state. So for density of state, what we have to do? We have to divide it by volume. So the density of states lying between kt and dkt will be rho kt dkt. We will denote it by this. This is what? This is the density of states lying between kt and kt plus dkt. So rho kt dkt. Okay. So this will be what? This will be n by volume. Because whenever we are talking about density, we have to divide it by volume. No matter what kind of structure we are talking about, we have to divide it by volume when we are talking about density. So uh, first I am putting the value of this n, kt, dkt, lx, ly upon pi. Okay, this was the value of this n. Now dividing by the volume of a cube is lx, ly, lz. This is the volume. Cancel out the things, those are cancelling. So Lx, Ly are cancelling out. The remaining thing we have to write as rho kt dkt. Okay. So this is the density of states we are getting. So I'm writing this there. So I'm getting that rho kt dkt equals to kt dkt upon pi Lz. Okay. This is what I am getting. Okay, now I've got this expression. The next thing what we have to do, next thing is we have to calculate the density of states in terms of energy. So in terms of energy, what we do, we'll have it like this. Wait a minute, there is slight problem in the settings today. Okay, so since we know that what, ki rho kt dkt will be equal to rho e de. This formula we have been using earlier also. So this is the thing. We have to find out the rho value of rho e. And the thing is same. How we will be determining it? Rho kt dkt divided by de. And in the next step, we'll be doing it rho kt by de by dkt. So this is how we'll determine rho e. Now we have already have the value of rho kt. From here we have the value of rho kt. Rho kt is kt by pi Lz. Okay, we have to find the value of de by dkt, and de by dkt we will be finding out with the expression of energy that we have already determined. We have already determined that EC equals to EQ1 plus h cross square kt square by 2mc. From here we'll find the de by dkt. So differentiate it with respect to dkt, with respect to kt, not dkt. Okay, so it will be de by dkt equals to, what we'll get, this is constant, so it will be 0, differentiation will be 0, only we'll be having this term. So h cross square twice of kt upon twice of mc, 2 will cancel out. This is what we will be getting for de by dkt. Now we'll put this value here, d by dkt, and instead of rho kt we'll be putting this value. So we'll write now, therefore rho of e. Now I'm putting the values in this. Therefore, rho of E is what? Put the value of rho kt. Rho kt is kt by pi Lz. So it will be kt by pi Lz. I put this value. Now I have to put the value of de by dkt. So de by dkt is this thing. So I'm putting it here. H cross square kt and taking this mc upwards. This like this. This kt cancels out. So what is remaining is that mc upon pi Lz h cross square. This is your density of states, or we can say this is the density of energy states lying between kt and dkt. Okay, this is the expression. Now in this expression you can see that there is no term of energy on the right hand side. It means we can say that the density of states is constant of energy. It does not depend on energy because there is no energy term on this side. We have effective mass of electron, we have pi, we have a Planck constant, and Lz is what? Lz is a reduced dimension, or we can say this is the thickness of your quantum well. Okay, so we said that this density of states is independent of energy. Okay, so now we will be plotting this all. So for this plot I am erasing this now. Okay, now we will be plotting it. So First we will be plotting in terms of energy. That is, I will be using this expression EC plus EQ1 plus H cross square KT square upon twice of MC. We'll be using this expression and I'll be plotting this. So in plotting this, what we have, this side we have KT and this side we have energy E. Okay. So in this expression, this equation is for what? When we were considering only the first ring, then we got this expression. Okay. So for the first ring, the value of, if you remember, what was EQ1? EQ1 was your H cross square KZ square upon 2MC, and here KZ for Q equals to 1, the value of KZ will be 1 pi by LZ. Okay, this thing you have to remember, that we are putting these things. This is EQ1 and KZ is this in this case. For the first ring, where? In this diagram, we are talking about the first ring, Q equals to 1. Okay, so now plotting this in terms of KT, what we have to do, when we are putting KT equals to 0, if KT equals to 0, KT is 0 means this whole term will be 0, then we have only E equals to EC plus EQ1. Okay, it means when KT is 0, when it is at origin, the energy value is EC plus EQ1. So if I mark this point as EC, I have to mark upwards, this is your EC plus EQ1. Okay, and now when KT increases, when the KT will increase, at the 0 position we have already marked the point, which point we will be getting. But when the KT increases, we can see that this is a parabolic approximation again. So the graph will change parabolically. It will go this way, both the sides. Okay. Similarly, for EQ2, if I consider the second ring, this one, for Q equals to 2, for Q equals to 2, EQ2, what I will be getting, instead of this Q1, I will be writing Q2 simply. So again at KT equals to 0, their energy will be EC plus EQ2 in that case. So suppose here is that EC plus EQ2. Okay. And again in this case also, in second ring case also, when KT increases, I'll be again getting a parabolic approximation like this. Okay. So what we call these bands we are getting in terms of energy, we call these as energy subbands. Okay, and we'll be getting 4 subbands because we are having 4 rings in the z direction. Okay, so these we call energy subbands of quantum well. We call them energy subbands of quantum well. Okay, so this is clear. Now the next thing, so now next we will be plotting the density of state, that is this expression we have, which we have already determined. The expression is that rho is equals to mc upon pi h cross square and what we have here, LZ. Okay, so this approximation we have calculated using the conduction band approximation, so I can write it rho c, because we are already talking about the conduction band, we are not talking about the valence band. So this is the density of states, density of energy states in the conduction band. So I'm plotting it for the conduction band only. So for this, what we will be having, we are having like this. Okay, so this is your energy and this is your rho CE, means density of states in the conduction band. Now, since we noted this expression we have got for Q1, EQ1, or we can say for the first ring, this expression was for the first ring. So, and we were having some value this, so we are saying that for the first ring, that is for EC plus EQ1. You can mark EC somewhere here. For EC plus EQ1, you are getting this value of on the scale of density of states. So let this value is here. So I am writing this value as mc upon pi h cross square LZ. Okay. Now let us make a dotted line like this. So this is what you are getting. Okay. Now the second thing is for the second ring. For the second ring, what will be? Let the second ring, the value will be EC plus EQ2. The value will be this EC plus EQ2, and this value will be twice. Means it will be twice of this. For second ring, the value of density of state will be twice. Why it will be twice? Because in this case, the expression go to again to this expression. Okay. wait a minute. Okay. So if you go to the expression, these expressions which I am saying, so you say that it is q equals to 1, we are getting this. So for second ring, we have to put q equals to 2, and for this kz will be twice of pi by lz. So it means automatically it will go to the twice thing. Okay. So that's why we are saying that it will be twice. So for the third ring, suppose the value is here EC plus EQ3, and the point will be thrice now for the third ring. So it will be pi h cross square Lz. So this is how we will be getting the points on the graph. But the thing that we should see is that we have seen that this density of state is independent of energy. When this is independent of energy, it means that we have this at this particular value, we have the density of state to this point, we have this value. Okay, but since there is no allowed state between the ring q1 and q2, that's why the density of state will not change when we go from q1 to q2. It will remain the same, it will remain constant, because there is no allowed state between the ring q1 and q2. So, and again on reaching point q2, it is eq2 on the second ring, we get the density of state because there is density of states available, we have this ring available at q2. So we get a value this twice. Again on going further, now like now I am going from q2 to q3. On going to q3, between q2 and q3 there are no allowed states, so again I am getting a constant value, and then I am getting the value that is thrice. And similarly I'll get for the fourth ring like this. So we get a step like behavior in the case of density of states in the 2D structure. This step like behavior we are getting for a quantum well, or we can say for a 2D structure. But whereas if I can see like this, if we plot it like this dotted line shows you what? This shows you the plot for a bulk structure, or you can say for a 3D structure. We can, if we draw the dotted line joining these points represent the bulk structure. And you can check this also by putting the value in the bulk structure instead in the value what we have got in the bulk structure. That is rho, the value of rho in that case, just simply put EC plus EQ1 there. You'll get the same value this. What I am saying is, let me tell you one thing. You can, why I have joined this point, why I have joined this dotted line over here, how do I know that? So for this, we can simply do that. Put the value of the, like for a 3D structure, you can do this exercise later. For a 3D structure, I'm just giving you an idea of that. For the 3D structure, we get that rho CE equals to 1 upon 2 pi square upon 2mc by h cross square path 3 by 2, and 1 upon here what we were having, we are having E minus EC by 1 by 2. So this was the value we were getting for a 3D structure. In this, simply put E, instead of this E, put EC plus EQ1 and then solve the equation. Also, you need to put the value of EQ1 later. So EQ1 we already know that EQ1 is this. Put this value, solve the equation, you'll get this rho CE equals to this value. Okay, so that's why we have joined these to the points. Okay, so this is the density. We have made the plots. So this is how we'll be plotting the energy versus density of state. The next thing is what we are getting when we are decreasing the dimension from the 3D structure to 2D structure. The energy band gap increases. The quantized value, we are getting the energy in the form of subbands, and due to this the effective band gap will increase. The effective band gap will be now what? Let me show you that. See, generally what we make in a EK diagram, in a EK diagram, let me make the EK axis. So this is your K, and we plot it like this. Okay, and this is for you, it's very familiar. This is the EK diagram, this is the conduction band, this is the valence band, and generally what we showed at the band gap is this thing. This is the EG. This is for a 3D structure. But when we are reducing the dimension, what we are getting in an energy scale, what we were getting in En versus KT diagram, we were getting the energy subbands. If you remember, we have just plotted it. Similarly, you will be getting this in the valence band also like this. Okay, so you can see that in the EK diagram, the case of a 2D structure, we were getting energy subbands. So in a 2D structure, the effective band gap is what? It is the difference between this first ring and the second ring. Means there will be four rings this side, four rings this side in our case. But the effective band gap will be the difference between the first subbands. This difference is the effective band gap, and I call it EG dash. Means it's a difference between the Q1 and let this be the Q1 dash. This we are getting for a 2D structure, these energy subbands. Or we can say that simply EG dash, that is the effective band gap, is EG plus EQ1 plus EQ1 dash. EQ1 dash means we have to use this value plus this value, and this value is the effective band. So you can see that in a three-dimensional structure the band gap is less, but in the two-dimensional structure it is quite big. So on reducing the dimension, the band gap also increases. Okay, this is one of the important conclusion of this 2D structure dimension, 2D structure formation. Okay, so this is here we complete our 2D structure. Next will be density of state in one dimensional structure. Okay, so we'll be doing it now. Density of states in 1D. So in density of states in 1D, we'll be doing it in short because we have already discussed 3D and 2D in detail. So in density of states in 2D, we are just doing what? We are reducing one more dimension. This was the dimension kz, y and kx. So initially we have reduced this z dimension. Now I am reducing this y dimension also. I am reducing this ky from 1 mm to 20 angstrom. Again the same thing which we have done to the z-axis. In z-axis also we have reduced it from the 1 mm to 20 angstrom. In this case also I am decreasing this y dimension from 1 mm to 20 angstrom. Now what will happen? We will again have the 4 allowed states in the y-axis. We have 4 allowed state in the z-axis now because we have already reduced it, and now I am reducing the y-axis also, so I am having the 4 allowed state in the y dimension as well. We can show it like this: first, second, third and fourth, because you have to show them like increasing. Similarly 1, second, third and like this fourth. Now the electron can have any state in the x direction, can take any allowed state in the kx direction, but in ky and kz direction there are only discrete values allowed because these both dimension have been reduced. It can take only some particular values in ky and kz direction. So in this case, what we will be doing first, in this case the area E will be, we have to write it like this, that EC plus EQ1 plus EP1 plus h cross square kx square upon twice of mc. Why we have written it like this? Because in this case, this we already know, this we have already done. But in this case, since the y dimension had been reduced and y dimension we were using the notation p. So this is for the first ring, p equals to 1. We are using for this. Okay, wait a minute. So this is the EP1 for this first ring, and this is the energy in the kx direction, because this can change, because x direction the electron can take any value, any allowed state it can occupy. So this is the energy in the case of the one dimension structure. Now what we have to do, this is the energy we have done with this. Now the total area, we will directly go to the density of state in this case. Total area. Now, since these both things have been, both dimension had been reduced, the only thing is this kx, that the structure is kind of what? It is kind of a wire now, because only one dimension is reduced. So we can say total area between kx and kx plus dkx. We have only one dimension now, so the total area will be like the area of a wire, something like that. So we'll be writing it like kx dkx. This is the area, total area between kx and kx dkx. The next thing is area occupied by one allowed state. Area occupied by one allowed state. So what was the area occupied by one allowed state? The area occupied by one allowed state was, it was your pi by Lx. Okay. So this was the area occupied by one allowed state. So the area occupied by one allowed state is pi by Lx, because the other dimension have already been reduced. So this is the total area now. Now the next thing is number of points, or we can say the number of allowed state between kx and kx plus dkx. That will be total area kx dkx divided by the area occupied by one allowed state. The area occupied by one allowed state is pi by Lx. Okay. Now since we are taking only the one dimension now we have the half of that sphere, which were initially we were taking as 1 by 8 in 3 dimension, then 1 by 4 in 2 dimension. Now for the one dimension we will be only taking half, because we will be considering the positive half axis of kx dimension, or we can say in the x axis we will be taking the positive half multiplied by 2. This is due to the, again due to the Pauli exclusion principle. So this 2 cancels out. We have this thing. So now n equals to your kx dkx. This Lx goes up upon pi. This is what we are having in this case. This is the value of n. Now we have to find out the density of states. So continuing with the density of states. Now what we have, for the density of state between kx and kx plus dkx, we will be writing rho kx dkx. This will be equal to your n by v. So the value that we have obtained from n is kx dkx, and this was Lz, and we were having a pi here, not Lz, this was Lx. Dividing by the volume, again the volume will be Lx, Ly, Lz. Okay. Lz. Now cancel out the terms that are cancelling out. This will cancel out, and what we will be having? We will be having kx dkx upon pi Ly Lz. So this is our, what we are having, density of states in the x direction that are available in the momentum space. Since we are talking about the k parameter, so it is the momentum states that are available between kx and kx plus dkx. And we simply cancel out this, we get the value of rho kx. So now the next thing what we will be doing, we'll be using again the same expression, that rho kx dkx equals to rho e d. This thing we have been doing from the past two structures also. So that's rho e will be what? This rho e will be putting the value. Now I'll be using the shortcuts, because we are familiar with all these things now. So rho kx divided by d by dkx. We need to put this value. And for dE by dkx, since we already know the value of this E is what? EC plus EQ1 plus EP1 plus H cross square kx square upon twice of MC. From here we will be finding out the value of dE by dkx. So the dE by dE, this is constant, this is constant, this is constant. What we will be getting? We will be getting this divided by twice of MC. Cancelling out this thing, we'll putting this value here. Okay. So putting out the value, what we get? Rho E equals to, we are putting the value of rho kx. Rho kx value is kx upon pi Ly Lz, and we are putting the value of dE by dkx. The value of dE by dkx is h cross square kx and MC. Okay. This kx cancels out. We get this thing. So in this expression, we have to see, we are getting a term Ly and Lz. What is this Ly and Lz? Ly Lz is the area of reduced dimension. Area of reduced dimension. And in our case, since we are talking about a only one dimensional structure, we are talking about a wire kind of thing. So in our case, the area will be what? So this area will be representing this area Ly Lz in our case as K. Okay, we'll be representing it by k in the momentum space, because this is a very reduced area. We can say this is the area of a small rectangle or a square. Okay, so I'll be putting, instead of this we'll be using k. So now we have rho of E equals to mc upon pi k h cross square. This is what we are having. Now, if we remember the case of this particle in a box in one dimension, we will know that in particle in box in one dimension, where the particle was allowed to go in x-axis only, we have considered this thing that k square equals to 2me by h cross square. Okay, and here we'll be using this value of k. So we'll finding out the value of k from here is root of 2me divided by h cross. We'll put this value of k here, so we get rho of E equals to mc upon pi root 2me h cross square, and this h goes upward. This h cross cuts, then we get mc upon pi h cross root 2me. So this is the density of states we are getting in one dimension. This is for 1D. So here it depends on energy. You can see it is depending on the energy. It is inversely proportional, and this is also in the square root. Okay. The next thing is what we'll be plotting it. So on plotting it, we can plot it like this. So this is your rho CE, because again we have taken only the conduction band approximation, and this is energy. Since we can see that if you increase the energy, this will decrease. Okay. And when the energy is zero, we are talk about this point. There are large number of states available at zero energy, because this is kind of a like the lot of electrons will be there with the very less energy. And when we increase the energy, the number of electrons decreases. So the graph will be something like this. Okay, as we increase the energy at high starting point, this will be zero. Energy is zero, we have the maximum value, but when we increase this thing, this will decrease. Or we can say when energy increases, since we are taking this on x-axis, we can say when this increase, this will decrease. So we have shown it like this. Okay, so this is the graph for the density of states in 1D. Okay, next we will be doing with the density of states in the 0D. In density of states in 0D, we will be not going and any detail, because in density of states in 0D, we know that since in this we can have to reduce the third dimension also. In density of states in 0D, in this case we have to reduce the third dimension also. So the structure what we will be getting in momentum space will be kind of this thing. Now you have kz, ky and kx. Only kx was remaining that we have not reduced. Now suppose now this kx also 1 mm to 20 angstrom. In this case, what we'll be having? We will be having the four rings here also, like this. This will be bigger one. And similarly, we have all the dimensions are reduced now. Now electron cannot move freely in any of the dimension. It is like it is trapped inside a box. Okay, so we call such a structure as a quantum dot structure. Okay, so there is no case space that is remaining to be filled with the electrons, and all the available state can take only the discrete energy. So in this case, we have simply write that density of state is equals to, this is the delta function, E minus EC. Okay, this delta, this is the delta function, and we'll simply plotting it like this. This is your rho E here. In this case, we have taken rho E here, so you can take like this, and this will be simply like this. Okay, this is what this is showing this. Then electron can take a particular value of energy. It cannot go here. There is no density of state available here. There is no density of state available here. It can take only some particular values inside that box in which it is trapped. Okay, so here we finish our density of states in 0D. In 0D, you simply have to mention that electron is trapped inside a box. It cannot go in any of the dimension. Okay, so we have to show like this. So here you can end up with all the things. And here is our density of state topic ends. Okay, thank you.